Welcome back. This will be tutorial 11, talking about multivariate processes. Before we start, I just want to remember you that we have a quiz that will be due on the 19th. So not this Friday, the next one. Same as usual, make sure you submit it before 4 p.m. And another thing that is probably more interesting and worth a little bit more is your report too is already available. It works the same way. Will be due on the 5th of June. Also, please submit before 4 p.m. unless you have any type of extension. Other than that, what else? Same scheme. Don't send too many. The source code, or if you have the output, if they are plots, try to think a smart way of showing it. Maybe you don't want to show all the plots you got, just the ones that are relevant. And if you have some information that is numerical, maybe you want to format it and put it in a table or something that looks like a report. But I'm sure, as an kind of an advice, you will see that during the second one, at least based on my experience, it's way easier after you had to do the first one, and it follows a little bit of the same path. So if my experience is any relevant, it will be faster to do the second one than the first one. Also, it will be all on multivariable, multiple equation, right? And you just have two tutorials dealing with multiple equation, which is this one and the next one. So I believe most of the things will come out of these two tutorials, and some other specifications, like some other theory, might come out of the other ones. But in terms of code, I would expect most of it to come from this two. So yep, good luck with it. What else? I think for admin, that is it. So for this tutorial, we will be using this money demand that we have under tutorial 11. So please download your CSV file, save in a folder as we usually do. And maybe you want to save the questions too. And you can use this address to download the code where I'm sharing. Let me copy it and share with people online. Copy link. I'll put it on chat. In chat, that's it. So if you click that, you should see something like this page here, code share. It's a little bit slow. I think I already have it open up in here. And you can select everything, copy and paste to a new script, save it in the same folder as you have. Let me do it live. I usually forget, but it's a good idea. I have it open in here, but let's create a new one. So create a new script. I have copied all the code. I will paste it here, as you can see. Now, important thing, in order for this set working directory to work, I need to save it inside of the folder I have the money demand. This is where my money demand is. I'll call it tut11 live. Save. That is it. Now I can close the other one. All right, let's go. We have the code. So today we're going to use R to construct an adequate set of var models. You will see the process is pretty much what we have been doing with ARMA models. Use R to forecast one of the variables generated by var-p processes. Derive a structural var from a reduced form var using Cholesky factorization or Cholesky decomposition. Use R to obtain inference on dynamic relationships from an identified var. And I will explain what each of these things are. Dynamic relationships is the same we had a look before in a RDL in tutorial 4. Then we saw co-integration tutorial 6, and I will see it in this multivariate processes, multiple equations situation. And finally, use R to obtain inference on Granger causality. So to start this tutorial, I would like to do a little bit of a recap on that. I'm not going to explain the whole thing. You will see we have over an hour of pre-recorded video and another 2 hours, or if you put together 4 hours of lectures explaining the motivation, where it's coming from, and etc. So what I'll do, I'll just pass over and just point a few things that are important to know, and that will be it. I'm not going super deep, right? So first, let's recap what vector autoregression is. Recall the ARDL. This is what we had before. So you have our dependent variable yt is equals to an intercept. And here I will put a minus, and later I will explain what it is. But it's pretty much, we have a contemporaneous exogenous variable zt. So it's contemporaneous because they're happening at the same time. They're not legs, t and t. Then we have a leg, an autoregressive leg of y, and then you have the same for z, and then the error, right? Simple ARDL 1, 1 leg for our dependent variable, 1 leg for one of our independent variables. So with the single equation, first we analyze dynamic relationships, but we didn't do forecast. And why didn't we do it before? Let me try to point out what happens. Let's try to forecast yt plus 1, so the next period. Look, yt plus 1 is equals our intercept, then our bzt plus 1, and then this, so z becomes zt plus 1, ybt minus 1 becomes yt, zt minus 1 becomes zt, and the error then we have for this yt. The thing is, we have all the information I have in black, but our data ends in time t, so we don't have this zt plus 1. So how do we do that then? How can we forecast this ARDL? What we do, we bring zt, instead of being an independent or exogenous variable, this comes to our equation and becomes a dependent or endogenous variable too. So now both yt and zt are endogenous, and they have their own equations. So this is how, now zt is also an endogenous variable. This is how we're going to treat, and this is how you're going to make forecasts for this ARDLs, or now that they are together, these VARs. So, all right, we have a VAR, we have both those equations, but you probably heard we're using structural VAR. I think it's important for me to explain, important to point out, these are slightly different things. Structural VAR is a specific VAR, and what makes it structural? Look at this. When I'm trying to estimate yt, I have to estimate everything that is in black, which are legs, so probably it's information I already have. But I have one contemporaneous guy here, zt. But when, okay, I haven't estimated it yet because it will be estimated in the next equation. So let's run the next equation first to estimate zt. I start working on it, and then you find yt. Like, oh, that's a problem then, because I need one to estimate the other one, and vice versa. So how do I do that? In fact, this is what makes a structural VAR. It has contemporaneous values that make it hard or impossible to estimate without imposing restrictions. So what I wanted to say, this is kind of a motivation to why we need these restrictions. So it is important. It is not possible to calculate unrestricted structural VAR. And I made it unrestricted in red. I put it in red just to make it very clear. This is what we're talking about from here on. One alternative to solve these equations is to impose a restriction on one of the coefficients, right? What is to impose a restriction? And I notice people asking, I don't think, so for some people, it might be harder just to grasp what is going on. And I think it's pretty simple to explain. Look, if I said that this coefficient B12 was 0, and saying, hey, algorithm, hey, Mr. R, calculate for me, but I know you're going to have trouble calculating this guy simultaneously, so please force this guy to be 0. What happens then? We are able now that we don't need the ZT, I can calculate all my forecasts in the future, but I need to calculate first YT, first thing here. Then with the value of YT, I can calculate ZT. But what are the consequences of imposing that variable? We will be exploring it more on question 2. But to initially, just to have a look what's going on, you will see that while ZT is affected by a contemporaneous YT, or which means if something happens to YT this, let's say, quarter, the same quarter ZT will suffer an impact. On the other hand, YT, if something changes in ZT, it won't impact YT in the same quarter. It will only impact ZT in the next quarter, when this ZT will be important for the next equation. So by imposing these restrictions, we make someone not react instantly to one variable, not react instantly to the other variable. This is a little bit the motivation behind the restrictions. And pretty much what I'm saying is we can solve this equation, right? So var is a group of things that not necessarily have contemporaneous contemporaneous parts in the equation. A structural var has contemporaneous, and usually if it's unrestricted, this structural var will have contemporaneous of all other variables and the same amount of legs of all variables in all equations. So a var 1 for these two variables is like this, has everything. But we will see later in our calculation that it's very easy to have a lot of coefficients for vars that initially look relatively small. All right. Another thing, so you saw that we were moving it to matrix form just to make it easier to see multiple equations without filling our screen with tons of things. So still our var 1, just one lag of each of the variables and two variables. Having it in matrix form, we have videos, pre-recorded videos for it, but I hope you can see what's going on here. We have just a little vector for this part here. We have a little vector for the legs, this, and this is multiplied by a matrix, which is just a combination of these coefficients. And the intercept is this gamma 0. So you will notice usually bold letters, or if it's Roman or if it's Greek, bold letters represent vectors and matrices. This is a common notation, usually in mathematics. And capital letters, this is a capital sigma, this is a capital gamma, sorry, will be matrix, while lowercase bold letters will be vectors. Okay, just basic stuff. But we can write this equation as capital B of xt equals to gamma 0 plus gamma 1 times xt minus 1, just the legs, plus epsilon t. What is going on here? And that's why we have the minus. You will see there's a video explaining it step by step, but pretty much if you move this minus to the other side, we will have yt z plus, sorry, b12 zt. This guy coming here, right? If you multiply in a matrix, this is how it works a little bit. Let me just use this. we multiply a line by a column. So this will multiply this guy, which gives you this. This will multiply this guy, which will give you this one. But after you move here, it becomes plus. So plus B12 ZT. Okay, so pretty much you can see for the first row, it is the first equation. For the second row, it's the second equation. But nothing special about this, nothing complicated, just moving and having it in matrix. Why matrix? Once again, just if we have multiple variables and multiple legs, it's a way to make it shorter. Okay, let's keep going. After moving to this matrix form, we will do the reduced form. The reduced form is getting this beta and moving it as a denominator, like dividing the other side. That's how I think about it. But pretty much it's the same as multiplying by, if it was a scalar, just a number, it will be the same as multiplying by 1 over b. But in matrix, it doesn't work like that. And we usually, in matrix, we draw it like we multiply this part by b minus 1 and multiply everything else by b minus 1, 2. But it always comes before. Let me go back. Okay, so that's what's going on here. When you multiply by b minus 1, b to the power of minus 1, times b, this disappears, becomes a 1. It actually becomes an identity matrix, but it's what you do to make it this guy disappear. And here, the b to the power minus 1, which is, let me use the proper word, is an inverse of the matrix B, or capital B. This is what's going on. It goes there. And then the reduced form, we're just calling b minus 1 gamma 0. We're calling it little a 0. B minus 1 gamma 1. We're calling this capital A1. So this is a vector. This is a matrix, right? And finally, our error, inverse b times epsilon t, will be the ET. All right? From here, as I'm saying here, this is enough to forecast. This is back to the format where we can do an ordinary least squares, or pretty much a normal linear regression, and calculate a forecast. To calculate forecasts or to analyze a few things. And this is easy to do, and it's pretty much what the software will do for us. So in terms of theory, I'll stop here, and we're going to do exercises, but I'll jump in the theory again to bring back those things we discussed, to expand a little bit towards all the details, okay? All right, so our data set will be money demand CSV, which contains quarterly observations, so by quarter, from 59 until 2001. For the real GDP of the US, nominal GDP of the US, the money supply, which we'll call M2, and the treasury bill for 3 months or 90-day treasury bill. We are going to transform them. So for the real GDP, we're taking logs of it. Then we will transform the money supply by first getting the GDP deflator, which is kind of so it's something comparable to a CPI, to the inflation. So price T will be GDP divided by real, nominal divided by real. And then we use this price T to divide M2, our money supply here in dollars. So we're pretty much correcting it for inflation. And then we take the log. And finally, our short term, we are just taking as it is. We're not taking a log of it because it's already an interest rate, which usually we don't take. We don't need to take a log. Okay, that's what we're doing. Let's go to R. All right, start by cleaning everything. You will have 2 new libraries there. One is VAS. For almost everything we're doing today, we'll be using VAS. And But there's also pragma, which is a package just to use a permutation of the order of our variables. We will just use it once to just make a combination of, there are 3 variables. We will put them in different positions. So this first, then this first, then this first, kind of split, whatever, what I can do with my fingers, do a mix of them. Then we're using zoo, vas, and pragma. Let's run them. You will notice that vas, it's not sending an alert, but it's masking a few functions. Then if you saved in the right folder, running this one will give you the current directory. Then we can load my data. You'll see 169 observations and 6 variables. So date, GDP, Rio GDP, M2, treasury bill, and then an X that is there, empty. So we're not using it, right? So read the lim, just the basic. Now let's create these variables with the information we have. First, date will be an as year quarter. So my data, $ date, it's getting like that. You will notice the date is in this format, is a dot 1, dot 2, dot 3, dot 4, 1, 2, 3, 4. Apparently, just run it like that will work for us. So if I printed date, this is what I would get, dot 1, dot 2, dot 3, dot 4. But now I understood it. So it transformed to this space quarter 1. So just by doing year to quarter, it already translates in a nice way. That's what zoo does usually. Then we have real GDP. We're already transforming it and taking the log of it. So L real GDP. Then for price, we are dividing the nominal GDP by real GDP to calculate inflation pretty much. Then the log of money supply will be the log of M2 minus the log of price, which if you're a bit, that's not exactly what they asked us. They are asking to take the log of dividing. You probably remember that this is the same as taking the log of, let's call it M2 divided by price. Remember, when you take the log, whatever you're dividing becomes a subtraction. So nothing new there. Finally, 3 months treasury bill, 3 months we're putting inside of this RS variable. All right. And then bind variables into our vector X. So this is something that we'll start doing. We will always have vector X, which vector autoregression. So pretty much this X stores our 3 or multiple amount of variables. So C will get a column bind. So getting all 3 guys and putting them together as columns here and here. I will run, and then if you want to print, oops, okay, I didn't run all the lines. Okay, now it should work. Nice. If you want to print, you will see the 169 observations like that, as we did, binding by column. Now let's print. Let's plot our variables. First, we have real GDP. You can see it growing, but it looks like a small number because we took the log, but kind of growing in a straight line. Then we'll have our GDP deflator, which is kind of a type of price in, I said inflation, but it's more like a price index, I think would be a better way of explaining it. So also kind of grow in a straight line, not necessarily, but you can see, I was going to say, this is not the, I apologize for that. This is not GDP deflator. Let me fix this one. This is actually our money supply. I'll fix that in the code later so you guys can download the correct one. But this is the money supply that we calculated here. Finally, our interest rate. Oops, you will see very small numbers, which is pretty much a percentage multiplied by 100. So here would be 4% and etc. This percentage, we don't take logs, right? Short-term interest rate. That's it in terms of data. We created the variables we wanted. And let's go. Consider the forecast. Consider forecasting a log of real GDP using var-p model of the multivariate process xt, where xt is equals to this specific order. And we will be talking more about order on the second question, in the second question. But yeah, construct an adequate set of var-p models. Let's go. 1a. We will consider vars with from 1 lag to 20. You will notice that it's not possible. The var function doesn't allow you to use 0 lags, but it's also something we don't use much. It's a very specific case. So pretty much what Eric's saying is that we don't need to worry about it. We create a list. So var estimates, it's a list. Then IC var, the information criteria that we usually save, that matrix with AIC, BIC, we will initiate it here. Just 20 rows because we're just doing 20 vars from 1 to 20 lags. Column names, the amount of lags, P, autoregressive lags to be more specific, then AIC, then BIC. So we are running for P in 1 until 20. Our var estimate, our list, will use this var function that comes from the vars library, and we add our x, which is our vector of variables, and also our p, which is the amount of lags we're running in that point, at that point. So after doing that, we will get the values for our matrix, which one will specify how many autoregressive lags we're using, and then we're taking AIC and BIC from our model. And as you can see, it's pretty simple. There is a function called AIC, of which in which you can just input the var model you have, and it will spit your AIC, archaic information criterion. Same for BIC, right? So let me run. You also see that the computation is pretty straightforward. There's no waiting time, super quick. And now let's sort by AIC and BIC. And I'll move to the slides so we can have a look. After running it, you will notice that 2, 3, and 4 lags are the top scorer for both our AIC and BIC. So we can move on with this model, these 3 models. So this is what we're doing in here. If you would print whatever I just showed you, you could print just this, guys, or you can click here and open it. But you get the same result, 2, 3, 4, and 3, 2, 4. Now we're moving on with this guy. So adequate set will get the matrix IC var, but just the second, third, and fourth rows, same as index, just 2, 2, 3, 2, 4. Run both. Now, what we're going to do is to test for autocorrelation of our residuals, which is the same as we were doing before for our ARMA models, but we're not using box test in this for var anymore. What we will be using is this LM test, which is the Bruch-Godfrey test. And let me show you how we're doing it. So number of models is the length of this guy, pretty much just 3 for the first run. And then we'll be running from 1 until 3. We will get, where is it? The amount of lags P, just to use it here to print first, checking var, and then we will do the test. We will do the test. Let me run it so we can have a look down there. What is going on? So we will print checking var2, checking var3, checking var4. That's what we're getting here. And then we're running this serial test to check the residuals. And we're calling it, we're asking serial tests to use the BG function. So Prushko free. If you want to have a look, it is here. Serial test vars. And the one we're doing is this one. A little bit complicated, but pretty much testing the null hypothesis is if these guys here, the coefficient, if you do a regression of your error on a lot of things, all the legs plus the residuals, if this coefficient is different than 0 for every leg of you that you want to test. Okay, that's what we do. Problem here. So the null hypothesis is that the errors, the coefficients are equal to 0. But we're finding, look at the p-values we're finding. Very small p-values. Therefore, we're rejecting it, which means there is a presence. These guys are probably different, statistically significant, different than 0. And there is a presence of autocorrelation then. So what I'm showing is this thing here, which means these 3 models that were our top AIC and BIC are not good enough. And what we're going to do next, since they are not good enough, we're going to do the same test, serial test, but for all of the models we have, from 1 until 20. Let me run it again. You see a very large amount of tests. And let's go from the beginning. For var1, very small number, reject. 2, 3, and 4, we have already rejected, and you can keep going. So like, okay, this is 2%, still rejecting, 3%, still rejecting. And finally, checking var8, 0.05967. So at least for a p-value of 5%, or 0.05, we don't reject var8. And going back, now I'm combining 2 information. Let me click here. This guy is good, 8, 9, 10 is not 5, but it's very close. And we've done it before. It is so close that we say, you know what, it's good for us. But why we will stay with 8, 9, and 10? Since if we keep going, this is good, this is good, this is good. All the other ones are pretty good, including say 15, 16, much better if it's just p-value, right? So why are we sticking with 8, 9, and 10? We are doing that because if you go back to the previous one, you will see that smaller legs are favored by both AIC and BIC comparing to large legs. So what we're doing is taking these 3 guys, the 7th, 8th, and 9th of the AIC rank, and the 8th, 9th, and 10th of the BIC rank. Okay, that's why we keep going with the just those 3. So let's go. And so white noise residuals are rejected, or if put another way, autocorrelation of the residuals is rejected for a certain amount of legs. Here's it's rejected for 7 or less legs, but it's not for an 8 or plus. So we're keeping on moving on with 8, 9, 10. All right, 8, 9, 10. So as a first question, we solved. We have our adequate set of vars. Now, how many intercept and slope coefficients need to be estimated for each of these guys, var p in the adequate set? So we have var 8, 9, and 10. You will remember that there is just a simple math to calculate it. Is the amount of variables. Here is the amount of legs. And so amount of variables times 1 plus the amount of variables again times the amount of legs. So if I run we have, oops, I need to run a few other things. This looks very small. I haven't run this once, so I'm still calculating for 2, 3, and 4. Let me run the adequate set again. We're choosing 8, 9, and 10 legs, right? So let me run it again. 8, 9, and 10 legs, 75, 84 coefficients, and 93 coefficients. Let me show you what we're doing visually. So this is the result, but I would like to come back to our 2 little equations that we had in the beginning to do it manually. So let's do it manually for our previous example. It was a var 1, so just one leg, for 2 variables. And look our number of coefficients. If k is the number of coefficients, it will be the number of variables times 1 plus the number of variables again times the number of legs. Pretty much what we did here. So let's count. For 2 legs, so 2 and 2. 2 and 2 here, sorry. And just 1 would be 2 times 1 plus 2 times 1. This is 2, so plus 1 is 3. 2 times 3, 6. Let's count. Notice that the question is asking how many intercepts and slope coefficients. So forget about counting the intercepts. They are not slopes. What we have, or we are counting, are these coefficients. So we found 6 in our math. 1, 2, 3, 4, 5, 6. So this is what we're counting when we're asked how many coefficients we have, okay? And the amount of intercepts will be the same amount of variables. All right, that's B. Let's keep going. So this is just the math that we just did. Check the stability of each estimated var P model. How does this affect forecasting? To check the stability, we're going to run another function. So once again, we get the number of n mods is the length of IDX var. It's still 3, the number of models. And we're going to do this for models 1 and 2, 3. We're getting the amount of legs, still quite the same as here. And we're going to print, it's a paste 0 to print var P, or 8, 9, and 10. A maximum absolute eigenvalue is, we're getting the maximum value of this calculation here. Roots from vars, var estimate P. So this function, roots, will calculate the eigenvalues for us, and we are just extracting the maximum one, the highest eigenvalue. So if I run here, one thing that I wanted to show you is that the vector it's using is, where is it? Is the companion form, the matrix, sorry, companion coefficient matrix. I just wanted to show you this part, but let's run it. Look, we got eigenvalues that are a little bit higher than 1. And this is a problem that shows our var is not stable, which for forecasting will be a problem if we're forecasting on the long run. There's a risk of exploding. So this is what's going on here. We found eigenvalues above 1. And if we continue, if we forecast for a long amount of quarters in the future, we can't really rely on those forecasts. But for a short amount, for a short period, it's not too bad. All right. Well, we keep going with these models. I just wanted to add here, what is the companion form? So the form that I showed you for that our var calculated, something like this, there will be an xt. This xt is actually a vector of our 3 variables, right? So we have GDP, we have money supply, and we have interest rate. So this is a vector, lowercase, bold letter. Then we have the intercepts. Then we have A1, which is a matrix. times this vector of the first leg of each of our variables. Then we have blah, 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 a2 times xt minus 2 until we have the apxt minus p, which will be for our var 8. This will be the 8th leg of each of our variables times this a8 matrix. What is the companion form then? From our reduced form, the companion form will transform our var p or var 8 or var 9, var 10 into just a var 1. And this will be a massive matrix that looks like this. So I'm not explaining how to get to this one, but I just want to point out this is xt. This is a vector, so it's not one value, but in our case, it's 3 values. So this is one vector on top of the other, on top of another, on top of another. So our 3 values for t, so contemporaneous, then the first leg of our 3 and the second and the third. Then we have all the intercepts, also one for each equation, also one and well, just for the first one, in fact, just the rest will be 0 vectors. Then this massive guy is our companion form matrix, and it will be represented by a tilde, a1 tilde. So it means we put all the a's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 into just one. This is a matrix. This is a matrix. So these are all matrices. These are identity matrices. So these are like just a continuum of ones in the diagonal and 0 in the rest. These are all vectors of zeros. So all zeros in here. Everything else in here is 0. And this is how complicated this matrix is and large this matrix is. Here is a vector of the first leg, a vector of the second leg, and etc. And here we have this matrix of ET that we calculated before. Okay, companion form, another format. And why do we need the companion form? So this is where our eigenvalues came from to determine if our var is stable. It was calculated as the eigenvalues are calculated from a square matrix, and this is the square matrix we used, this one, and they returned eigenvalues a little bit above 1. Okay, just wanted to make the connection. Let's go. Now, finally, the most interesting part, which is actually forecasting our log real GDP for 12 quarters past the end of our sample. Plot the point estimates along with a 95% predictive interval. Interpret the results. So let's go. Pretty much roots gets the eigenvalues. Let's go for D. Now you'll see that it looks a bit smaller. It is. And our horizon will be 12 quarters. Probably for your assignment, it might be a different number. Then we create a list of forecasts. So just a var forecast receives a list. Then for the X limit, we're going to force how long our plot is going to be. What do we have here? Look, it will be C. There's a minimum value and a maximum value. The first one, I will start by the maximum, which is pretty clear. We want the X limit to be the end of our date. So how long our date goes for, which we have date. We have 169 observations as we have for the other ones. So 169 plus horizon. Our horizon is 12. So 169 plus 12 would be 181. There we go. 181 is our last X tick. I think in the camera will be this way. Our last point. Now, how much back will we have? We will get the same 169. Look at this guy here. And we'll subtract 3 horizons of it. So if horizon is 12, 3 times it will be 36, right? So if 169 minus 36, so we start our plot in the observation 133. So with in our dates, it will be 36 quarters before, which is 9 years. So we're printing 3 horizons, and then we'll forecast another one. So this is what our plot is going to be. This is a way to, if we put a 0 here, it will print the whole data, then the forecast. But the forecast becomes really small because we have 169 observations for the data, and we're just forecasting 12. So this is a way to summarize a little bit how much we're doing. And we've done it before with the X ticks that you guys probably face from our previous tutorials. That's it. Then Y limit. Now let's set the Y limit, how tall our plots are going to be. This is also interesting because we're going to set a maximum so all of our plots have the exact same measure. So it's easier to move from one to the other and see if changes are happening. So for that one, we're getting the X limit of the log GDP. So the bottom of our log real GDP, the minimum value, and we're getting the maximum value of log real GDP plus 0.2. So we're getting a little bit of giving it a little bit of a margin in case our forecasts go further up. That's what we're doing. But I think with all of this, maybe I should have run it already so you can see there what's going on. So, well, let's go. Sorry for that. Let's go back a little bit. So just we're forecasting 12 from 169 was our last observation, forecasting 12. Y limit, we get equivalent to 3 horizons here and 1 horizon to the right. Y was up to here, but we added 0.2 limit up. This is the 0.2 there. Now, for 1 until number of models, 1, 2, 3, we're getting how many legs we get that, which will be 8, then 9, then 10. Then our forecast, var forecast, will receive, look at this, we're using a predict for our var estimate. Pretty simple thing. A number ahead is horizon. This predict is coming from our vars, so it's a special type of predict. Let me see, where is it? Vars predict. So this is the guy we're using, and it's taking our var to make the predictions. Number of ahead will be our horizon. And the model is just we take our var estimates and get the number of legs we just extracted, depending on the order of models, right? Then we're going to plot. And also this plot is also coming from vars. Maybe I can already put a vars plot. Whoops, that doesn't work like that. Okay. Plot, there are many. Just vars CV fun chart. Oh, yeah, this one. All right, so var forecast names LR GDP, log of real GDP, X lim, Y lim, the ones that we had before, and we're going to paste in the main forecast log real GDP. And then I added this little bit to the solution, just this part here, saying that we're going to have the var in the names. So that's why you can see, look, the forecasts look pretty much the same. It continues going up in the future, and the 95% confidence interval is shown in there, right? For the predict, it's already choosing the 95% automatically. It is probably a standard amount. Let me go back to predict. Look, CI 0.95. It's already the default, so you don't need to change. But if you're asked to do a different confidence interval, you can put CI equals 0.68, for example, which is a common one for a few different things. And that's it. That's what we get for the plots. So let's go back here. That's what we did. And look, we have RRB here with the log of real GDP. The plots, and you will see that they are pretty similar despite having this eigenvalue that was 1 point something. It didn't explode anywhere. So we can be pretty confident in our models. They don't have a lot of things different. And this is pretty much how we forecast using VARs. Let's see if I'm missing something. They are still quite accurate in the sense of having relatively small predictive intervals, but keeping in mind that these do not take into account estimate uncertainty. All right, this was question 1. Let's go to question 2. And for that, I want to remind a few things. So as I said before, it was enough to use our reduced form to do of our structural VAR to do forecasts, but to estimate impulse response functions or forecast vector error variance decomposition, FEVD, kind of acronym, FEVD. To do that, then we can't rely only in the reduced form. We would need to do a little bit more. So remember the restrictions I showed you for a structural VAR. We will need them to find the value of B, this capital bold B, so we can calculate impulse response functions and forecast error variance decompositions. So pretty much when we calculated our VAR, we got this reduced form here. So that's what we were calculating, and that's what we have, the A1. But now we will need to impose some restrictions so we can go back in the equation to recover our structural VAR equation. So we need to know the beta -1 and the rest here, which, as you might remember from the lectures, from our reduced form by itself and without any restrictions, we can get many betas. There are many ways of moving from here to here. So there's no one right way without imposing restrictions to get this amount, right? Remember, adding 1 0 helped solving this one. When we're talking about Cholesky factorization, or we are doing this, but for multiple many variables, right? A big amount of variables. So this is one of the ways it could look like. For the first variable, we will only leave the coefficient with itself. No, itself, sorry, just the first leg, something like this. But we're imposing zeros for the other ones. And what does it mean, as I explained before? So for this first one, it means that it's only affected by past values of the other variables. Then for the second one is only affected by past values of the other variables plus current value of the one above. And this continues for the rest of the rows. It means this one is only affected by past of the other ones, and then this one's affected by contemporaneous of all of them. Try to think what's going on there. For example, GDP, it's kind of slow to react to things. It's not something that explodes from one day to another, right? So it makes more sense to have it on top, while the stock market reacts to anything, and it's usually like a violent reaction. Makes more sense for these financial markets to be more in the bottom. All right, this is a little bit a way of thinking, slower and faster moving things. Okay, that's it. Not going further than that. So let's do it. Analyze the dynamic relationships between the log of real GDP, log of money supply, and real and interest rate. For all var specifications relevant to this question, please use p equals to 8. So we're focusing on just one of our vars, but with 8 autoregressive legs. Using the Cholesky decomposition, compute the impulse response functions for all the possible orderings of the system and study the responses. So all the possible orderings, that's where our Pragma library will come with the permutation. So like getting 3 guys and putting all the 6 possible variations of order. And are the responses sensitive to ordering? Choose the most reasonable ordering and explain your answer. So one step back, this is what we're trying to do. We will have GDP here, interest rate here, and money supply in this one. And then the next one will change the order. And then we will analyze these impulse response functions and see if we can get some conclusion out of it. Okay, just to put in context what's going on. So back to our code. Here we go. A. Look how it is. 1. Orders will receive this permutation from 1 to 3. Pretty simple thing. Look at it. Look at it. So here we're telling it, use the third one first, then the second one, then the first, and the other one. You know, permutations is pretty much 3 times 2. Here solves our equation, which equals to 6, right? 6 possible organizations of these variables. Then V names will receive log of real GDP, log of money supply, and interest rate. And this will be going, this is what is going changing orders. Then let's go. First, I is the response, the variable we're using for a response, and J will be the shock. So from 1 to 3, 1 to 3. First, we will create a title. So in each of these orders, we will then use the number of rows orders and create title of IG. So let me try to rephrase it. This is the shock going on, and this is the response of the shock. So for one shock, let's put for the response of one variable to one specific shock, we will do everything 6 times, each time with a different order of variables. Okay, so that's what's going on. So we have an I, a J, and a K rolling for the nested fors. So first, let's create a title. Actually, once again, before I forget, let's just run it first. And then this will be the longest one because it will generate 3 times 3 times 6 plots, which is quite a lot. So one piece of advice, you don't want to put all of this in your report. It's just pages and pages. You will see the solution for this tutorial, how long it gets. So yeah, choose wisely. All right. So the title is what we're creating here. Have a look. Response of LRM2 to a shocking LRGDP. You will see that soon it will change. Yeah, LRM and LRM. And then we have, so response of var names I, var names J, V names J. Then X equals to paste the order. So we're using the order. And then collapse equals to L. So we're separating the order with a comma and a space, and then we close our bracket, and that's it. I think this extra thing here is a mistake. We didn't need it, but that's all right. Then here is where we calculated the IRF, the impulse response function for this specific value for I, for J, and for K will be calculated. This function IRF, once again, coming from our vars. Okay, impulse response function. And then we have the model of which we will get an X, but we're sorting this X with the order of variables set by K. and we're only calculating this var for 8 legs. So just one model. So this X here is coming out differently depending on the order of the variables. What we're doing is it's a little bit of a dance of which variable comes first, okay, in the X. The number ahead, we're doing an impulse response function for 40 quarters, so pretty much 10 years. Response will be I, as we said, I is the one carrying the response. And impulse, the shock, is caused by J. So J is here and J is here. Then boot equals to true is doing a bootstrap. So it's calculating our bootstraps, calculating our confidence interval based on bootstrap. So 95% bootstrap confidence interval, which bootstrap, it's just something that calculates with the values of itself. It resamples. It's just something you don't need to know in detail, but it resamples the values. So that's how it's calculating our confidence interval. And then finally, it plots our IRF with the title we just created before. This little cat here was just the guy running in the bottom here, so you can have an idea if how much it's progressing. And that's it. That's what we just saw. And look at these responses. So many, right? I think 54 to be exact. Let's go here. So I just explained, went through the algorithm, but let's go through a little bit of analysis of what we have there. First, I put together inside of the same slide all the permutations of the data for a response of interest rates to a shock in money supply. So we are simulating, everything is like keeping a value. So we're simulating a little impulse or a little shock in money supply. It's not permanent. No, it doesn't go up. It continues. It's just up and down. And then we see how interest rates react to that thing, right? And look at these two guys here. So both of them, as a first variable, has log of real GDP, right? Here and here. But the order, of course, changes. And look how the reaction happens. Remember the Koleski decomposition. If we have the log of real GDP, the log of money supply before interest rate. So interest rate will react contemporaneously to the impulse, to a shock in money supply. So you can see it is not zero. It's far from zero from the get-go, from the beginning. But if you swap these two guys, it starts from zero. So when you go back to Koleski decomposition, you will remember that if one variable comes first, then it doesn't react contemporaneously with the next one. At least if your Koleski is just that perfect lower triangular thing. So just to refresh your mind, we had GDP here, but this second guy doesn't react contemporaneously to the third one. But the third one reacts contemporaneously to the second one. So that is what we see in here. Right? So this reacts from the beginning and this doesn't. This is the difference. Now let's look at another one. The response of interest rates to a change in GDP. Have a look. You will notice this changes a lot. GDP here is the first one. So the response of interest rates to a change in GDP, when GDP is the first one, which means it comes before interest rate, it already starts much higher, and then decays. And when GDP is the last one, so it comes after interest rate, it starts from 0 once again, and also the size of the shock is smaller. So although all of them pretty much look like the same, you start noticing these small differences. And when you're doing your report, try to see if you can catch something small and to present to us. But yeah, avoid showing all 54 models. I don't think we need to see all of them. Okay, because it will be pretty much, let me see if I can show you. They are very similar. So there are 6 of them. So look, for the same response to the same shock. Look how little they change. Now look at these guys. Dun, dun, dun. Oh, let's go for these ones. You will see that just the Cholesky decomposition, the restriction we're imposing, is what changes in the beginning, but it's not a huge change. That is it. So this is one way of interpreting. So what do we conclude about it? Quite of a massive answer there. But one thing that I wanted to call your attention. So here, it's pretty much what I just explained is what is explaining these 2 first items. The third item is saying pretty much similar, but I wanted to call your attention, come back to the order of the variables. A conventional approach is to have whatever is policy. So a politician decided something, which is our interest rate, for example. Place it in the middle of your variables. Then the slow-moving variables, which are the ones that don't react contemporaneously to the shock, you put in the beginning, before the policy. So all slow-moving variables are ordered prior to the interest rate variable, or whatever is a policy. And all fast-moving variables are placed after. So if you had stock market, definitely down in the list. If you had something else like asset prices also down the list, you will see them talking about it. So typically fast-moving variables are taken to be financial indicators and asset prices, whereas slow-moving variables are related to real economic activity. It's not like a change in the stock of one company doesn't really change the amount this company produces throughout the year overnight, right? These things tend to take a little bit longer. So slow and fast moving. Usually GDP is slow, but for our monetary money supply, it's less clear on how to classify money supply. Just calling your attention to a little bit of the details. So since from our impulse response functions, there isn't a clear indication of what order we're doing the variables, we will use our economic knowledge to get somewhere in this order. All right, that's it for the first question. Now B, using the ordering chosen in part A, compute the FEVD, so forecast error variance decomposition, and comment on your findings. You will see pretty simple here. For the FEVD estimation, we will just run this little function. I'm not showing again, but of course it comes from VARs once again. And we're just using our VAR estimate with 8 legs and 40 things ahead. 40, I was going to say 40 quarters ahead. And we're just using the original order that we created here. But if you ask yourself, oh, why you're not defining it anywhere? It's just because it is the order we created. Our X in here, GDP, then money supply, then interest rate. So we don't need to change anything. And so let's go. And then we're going to plot. this is what we get. Very simple. FEVD did pretty much everything to us, for us. 40 quarters. And there is a little bit of detail here. So the margins and where this little guy goes, we're editing it a little bit. Let me show you why. If you just plot it by itself, it is not really friendly. Maybe if you do it a little bit, if you do this, still not really cool. If I maximize, you'll see borders are not really nice in this factor forecast error variance decomposition. So we're setting some variables. You can play around with this one. This is probably the best one that has been found, Eric found or someone else. And it continues like that. You can change some values. Let's see what changes if we run it 0. We're reducing the margins even more, even further. This one, I don't know. Yeah, maybe we don't want to do it that far. But yeah, this is pretty much what's going on there. Let's go back to probably the best organization. What do we have here? Let's interpret it then. When we decompose, let's read it in the opposite order. The error variance of our forecast. Look at that. In the first quarter, the errors pretty much the errors from our forecast of log of real GDP are pretty much defined by itself, log of real GDP. But as it progresses, you will see that the money supply and interest rate becomes more relevant on defining that error, up to a point after a certain amount, let's say 40 quarters, that interest rate is responsible for almost half of the error terms in our log of real GDP, right? So pretty relevant defining. Money supply, not so much, increases a little bit, gets some relevancy, then lose some relevancy later on. Then when you look for money supply, it is the same. The first one is pretty much defined by itself, but then both GDP increase in relevancy, and it starts more after 11, 12 quarters, and interest rate starts increasing relevancy, reaches its peak after 2.5 years, second or third year here, and then it loses a little bit because GDP starts increasing. Finally, for the interest rate, it's pretty much defined by itself. Very small influence from our money supply and a little bit of influence that grows from GDP up to the third quarter and then plateaus somewhere here close to, I would say, 20%. Okay, that's how we interpret. So, and this will be important for the next question. GDP impacts money supply, quite some, impacts a little bit of interest rate, and of course impacts itself as expected. Money supply impacts itself, impacts a little bit GDP, and impacts, it's responsible for a little bit of the variance, like almost none from interest rate. Finally, interest rate is really important for itself, a little important for money supply, and quite important for GDP. Okay, so that's what we're getting here. A little bit of explanation there, and this is how you explain what's going on with the forecast error variance decomposition. We can go now to see our last question for today. So, obtain inference on Granger causality among GDP, money supply, and interest rate. So let's run this code. Also a very short code. We're just doing I in 1, 2, 3. It could be n mods here that we have used before, but just the 3 models. We're using this function causality. Guess where it comes from? It's VAS again. For our vector 8 of our var 8 legs, and we're choosing the cause. So this little, and we say this, GDP Granger causes blah, 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 the rest of the variables. Just by, inside of causality, just by choosing one variable, it will be analyzing Grange cause the rest of them. Okay, that's how it works. And then we print it. We're just printed here. So look what we get. So LGDP, the null hypothesis of this one, it's LGDP, do not Granger cause either money supply or interest rate or both. That's what we're looking at. What are we doing with this null hypothesis? Are we rejecting it? 0.009689. We are rejecting it. So it means we can say, since we reject, so we reject the null hypothesis in favor of the alternative hypothesis, which is RGDP, Granger causes LRM2 and RS. For the second one, we do not Granger cause. Let me click now. We do not reject. So we can't say, we don't have sufficient evidence to say that money supply Granger causes GDP or interest rates or both. And we reject the null hypothesis, so we can say that interest rates Granger causes GDP and money supply. That's what we're saying in here. And look how interesting it works with the previous one. So we're saying GDP causes the other two, interest rate causes the other two, but not necessarily money supply causes the other two, which is very similar to the conclusion we got in here. So GDP, it's kind of has a relevant impact in the error variance for the other two. Maybe here's a little bit small, but still 20%. Interest rates, pretty large here, pretty large. Interest rates is the clear one. So pretty large here, relatively large, maybe somewhere close to 20% here. And finally, money supply, pretty small. Look, maybe 10% in here and almost irrelevant there. So we're not surprised based on our FEVD. We're not surprised we're getting these answers for Granger causality. Does it always work like that? Not necessarily. As per usual, some things we can have some visual clues, but we still need to do the formal test, and Granger causality is the formal test. Okay, I'm sure it will be asked in your assignment. I need to double check the questions, but it's probably there. So good luck with this one. Also, yeah, there is this little guy here. I added one of our slides saying if our var is stable, it's very simple. What we're doing is just testing the coefficient. It's the linear hypothesis F test that we do if all coefficients are equal to 0. If one of them isn't, like the combination of them, we will reject the null hypothesis. Okay, so that's it. So today we use R to construct an adequate set of var models. We use R to forecast one of our variables generated by the var processes. In this case was the GDP. Then we derived our structural var from the reduced var using our Koleski factorization. Then we use R to obtain inference on dynamic relationships from an identified VARs, and finally use R to inference on Granger causality. Thank you so much once again, and I'll see you for the next and last tutorial next week. Have a good one.